the team services team, and we support all of Microsoft as they're moving over to Git. And specifically, some of them have some really interesting scale requirements. First off, let me just give you a bit of a picture of sort of as a whole what the company's been doing. Last year at Git Merge, we talked about how we're all moving towards a unified engineering system with Git at its center. And at that time, I think we had something like 18,000 developers who were using Git on a regular basis. And over the last year, it's roughly doubled in size, in number. And most of this is just small teams, medium-sized teams migrating to Git. They're using our Git service. We've been building up a build infrastructure, and most of the pain that they have is around updating their own tools and educating their developers. And there's some pain as they migrate over, but across the board, once they get there, you ask them what they think about it, and the answer is they would never go back. So the transitions have been quite successful. But we're about to get a major uptick in the number of users here because we have a few teams in the company that are just really large. And they are also interested in migrating to Git. So it poses some interesting scale challenges for us. For the past couple of years, the largest repos that we've had have been about the size numbers you see here, which compared to one of the larger repos out there with the Linux repo, our own team, the team services repo, is fairly large. And we have a handful of repos about this size across the company. And so we have 3 gigs this is 3 gigs of sources in the working directory at the tip of master. So this is not with any history or anything. And it's something like 350 developers who push to this repo on a daily basis. And so we've had to do a lot of work on our service to make sure that we can scale to this size of a repo. One really interesting thing that we've built is a feature that we call limited refs. With this many people in a repo, you figure each person is pushing 5, 10, 15 topic branches. Sometimes they remember to delete them when they're done, and sometimes they don't. And you end up with thousands of branches in this repo. And it just makes it a pain for people to work with it. When you clone or you fetch, you have to fetch all these branches that you don't care about. You try to list your branches, and you got to wade through a bunch of noise. It just slows everything down. And so we built this feature called limited refs so that when you clone or fetch, we filter down the set of branches that you see based on your identity. And so a repo admin will go and configure the set of branches that are interesting to everyone. So like in our repo, we have the master branch and then releases / a bunch of different names. We have a release every sprint. And those branches are interesting, but I don't need to see all 350 people's topic branches. And so when I clone, I see all the release branches and master, and then I see any branches that I created. Plus, I can go to the web and I can favorite another person's branches if I want to see them. And so that just helps us manage the sheer number of branches. And we've done a lot of things of that sort to make sure we can scale out. We've had to make sure that our pull requests can keep up with that many people merging into master on a daily basis. Had to get smarter about caching content. And we've done a pretty good job. We have several repos about this size, and they're working reasonably well. And the nice thing is, on your dev box, Git still does pretty well with repos of this size. The problem is this is not really big. This is big. So I have the Windows team coming in to a Git repo, and their numbers just dwarf everything else we've ever worked with. So now, in the working directory at the tip of master, you have 3.5 million source files, equals about 270 gigs of sources. When you clone, and this is with no history yet, you have an 86 gigabyte pack file in that initial clone. The index file, which has a cache of every path of every file that's in the repo, is about 400 megabytes in size. And so that just makes everything you do locally just a pain. Because so many of the local Git operations have to deal with the whole index. They have to read it in, scan through it, make a change, write it back out. So that's really painful. Now, luckily, our service, we've had to keep, this has pushed our service even harder, and we've had to make some changes, but we've been able to keep up. But all of that is kind of moot if the client experience doesn't work. So you try to clone this thing, and I wrote 12 hours, but it's kind of a lie because it's 12 hours when it works. If you lose your connection at some point in there, you got to start over. I think the last time I tried to do it, it took me 4 days to clone. And then, you try to check out that first branch, and it takes 3 hours. Every time you run status, and if nothing has changed in the repo, and you run get status, it'll take 8 minutes to tell you that nothing changed. And this is on an SSD. And say you edit one file, and you do a git add and then a git commit. It's 15 minutes per, which is the 30-minute number I wrote up there. It's just not usable, right? Not even in the realm of sane. And so we tried a bunch of different things to make this better. We played around with the idea of using an alternate object store. Git already has this concept of when it tries to find an object, it looks in a few different places, right? It looks for a loose object in the .git objects folder. It'll look for a pack file in your packs folder. And then if you configure an alternate path, if it doesn't find it in those places, it'll go look in that alternate path, again, for loose objects or pack files. So we thought, what if we configure an alternate path that we map to a network share, and we have a network-mapped array of hard drives that have all the objects already on them, so when you clone, you don't have to download the objects. You already have access to them. We hit in a lot of the sorts of tricks that we try to play on Git, we came up against this problem that Git made a lot of assumptions that are perfectly reasonable for a normal-sized repo. And then we're trying to push it way beyond those limits, and those assumptions break down. And so like with alternates, Git assumes that you're actually pointing at another local path, so it doesn't bother caching anything, because it figures the files are easily accessible. And so you try to access objects, and now it's doing random access I/O on a file that's on a network share, and so the latency is awful. And it still tries to, you clone, and it doesn't copy any files locally, but it still wants to make sure that it's all valid, so it still reads through the whole thing. And it just doesn't really work out. We tried taking this giant repo and splitting it up into a bunch of smaller ones, and then having some other tooling that kind of stitches them all back together when you want to build. And that just, it works for some limited scenarios, but it causes a lot of pain. For one thing, you can't ever do any massive refactoring, and that's something that the Windows team is very interested in doing. Because if you try to refactor across those arbitrary boundaries, you introduce a lot of pain in your developer workflow. We even looked at things like LFS, and LFS doesn't really make a dent in this problem. You can reduce the size of that pack file a little bit, but it doesn't reduce the number of files in the working directory. It doesn't make the index any smaller. So we realized that we have to kind of step back and think of this problem differently. And so the idea that we came up with was to just virtualize the file system underneath the repo. So that's what I want to get into in some detail here. We built this file system now on, for now it's on Windows. We're looking at expanding that. But what we do is we virtualize the whole file system beneath your Git repo so that it looks like all the files are there. And we play some tricks on Git so that Git doesn't bother looking necessarily at all the files. And then we download the files on demand when you need them. So now all of a sudden, your Git operations on that same repo look very different. It takes a few minutes now to clone. And that's the one command that we changed was we have a new verb, gvfs clone, instead of git clone. Everything else, you're just using regular Git on top of this file system. And so we can clone in a few minutes because all we're downloading is a commit object and all the trees, which all of those objects are tiny. And then from the trees, we can project the whole working directory. We know the shape of all the files in the repo. So clone takes no time. Checkout is a lot faster. And most of the time of the checkout is actually dominated by writing the index. Status, because we limit what Git will look at. Git has this existing feature with the sparse checkout, and we are pushing that feature beyond what it was designed for. With the sparse checkout file, if you list a set of paths in there before you do a checkout, Git will only write out those files into the working directory, and it marks everything else in the index as ignored. And so then when it does a status or a checkout or whatever, it only considers the files that it thinks it wrote out. It assumes that everything else was not even written into the working directory. And so what we do is we actively manage that sparse checkout file. And every time you hydrate a file, we write it into the sparse checkout. So Git just happily thinks the rest of the 3 million files don't exist. It doesn't bother looking at them. And that's how we get a fast status. We still have some bugs with these things. Like sometimes Git will decide like we just hit a bug where you run Git status and it takes an hour and a half. And it's because it kind of went down a rename detection path that caused it to start downloading lots of blobs everywhere. And we're fixing all those sorts of things. So we're not done yet. But we are seeing numbers that now are in the realm of possible, and we're still trying to make these faster. I'm also excited to say that it's all going to be open source. I mean, actually, as soon as I get off the stage here, I'm going to go publish these links. Don't bother going there just yet, but it'll be live in just a few minutes. The only URL that you have to memorize is that top one. If you go to aka.ms/gvfs, it'll take you to the blog post I'm about to publish that has all the rest of the links in it. And so the GVFS client-side code is all going to be open. We also rely on a kernel mode filter driver that we're trying to figure out the best means of releasing that. It's available if you want to test it out as a pre-release preview, the driver is. But the code for GVFS itself is available. The protocol that we use to get objects on demand is one that any service could go and implement, and we've documented that. We've also been making some changes to Git itself to work nicer on top of GVFS, and so those patches will be available in our fork of Git, and we're working on submitting all of those upstream. So let's talk about how GVFS works. The first thing I already alluded to is we have a file system driver, and it's made up of two components. There's a kernel mode component and a user mode component. The kernel mode part of it doesn't know anything about Git. What it does is it allows you to create, this is an NTFS extension, basically. And it allows you to have a folder on disk that is only partially populated. And then when you try to enumerate it, it will ask a user mode application to enumerate the contents of that folder. And so that's where we come in, is we then go and examine the Git trees and figure out what objects, what subfolders and files should be enumerated into that folder. And then one of these virtual files that are being shown in the directory, when a user tries to open them, when you use your IDE or a build tool opens it or whatever, that kernel mode driver will then ask our user mode process, give me the contents of this file. And we'll look in our local .git cache, or we'll ask the service through the protocol that we've got, and download the contents and write it into the file. And after that, it's just a normal file on disk. The other thing that we do here in our user mode part of this is we manage the sparse checkout, right? So when we hydrate a file, we get asked to write the contents of a file. We know that from then on, this is going to be a regular file on disk, and we're not projecting it anymore. So we put that file into the sparse checkout and mark it up in the index, so that now from now on, Git will own that file. Git will, when you do a checkout, it'll update it. When you do a status, now that file might be dirty, so Git will look at it. And that's how we make sure that all your Git commands work properly. We've also added a new feature to Git called the read object hook. So I mentioned before that when Git is looking for objects, it looks in the .git folder, the .git objects folder for loose objects, and then it looks in its packed folder, and then it looks for alternates. And finally, if it doesn't find the object in any of those places, it'll call this new hook, if you have one registered, to find that object. And so we have one registered where we will go and download that object from our server. We've also been making just general optimizations to Git. Again, it's one of those things where Git assumes that you have a full repo that's reasonably sized and all local. And so the one example of a change we had to make was after you do a checkout, even if your sparse checkout only has one file in it, and it just had to write that one file a disk, Afterwards, it tries to make sure that your repo is healthy. And so it'll scan through all the trees and all the blobs that are referenced by that commit and just make sure they all exist on disk. And when you're in a virtual file system, just checking that they exist means you're opening them, which means we're downloading them all. So we've made some changes there to avoid doing those sorts of checks. And we've added a config setting that you have to turn on in order to get these new behaviors. And so when you're on a GVFS-backed repo, Git just plays a little nicer with that design. We've also made, to make all this work, we've created a new protocol that I talked about. It's just an extension that you can go and ask for a single blob or a single object. You can also ask for the sizes of blobs. We need that when we're enumerating. And one thing that you really need to make all this work, one trade-off that we're making is because you're not downloading everything up front, you're downloading the files on demand. We're creating some extra latency in accessing those when you access a file the first time. And that latency really adds up. Like if you do a clone and then you try to run a build that touches 100,000 files, and on every single file you're making a call to the server to download the contents, that just really adds up. And so in order to make it all really work for the user, you really need to cache those contents close by. So we built a cache server. It's just a caching proxy for that protocol that we use. But it really makes things a lot nicer for the user. And we've been making a lot of these changes that actually benefit all Git users. Like these are just a list of pull requests that we've submitted already that just make Git faster in scenarios, and it's not even related to GVFS. So let's show you some of this in action. And earlier, the Wi-Fi was kind of in and out, so we'll see if this works well. So first of all, I'm just going to show you, and I'm going to demo this with the VSO repo, not the Windows repo. So this is that repo that's about 3 gigs in size. And I've got here, I've pre-cloned it in 2 different ways. What happened? I don't know. The connection seems to be lost. Can we get some help on this? Let me unplug it. There we go. When in doubt, just reboot it, right? OK, so I've got 2 copies of the VSO repo that I've already cloned ahead of time. One is with just regular Git on NTFS, and the other one is on GVFS. And I just want to kind of show you. So the NTFS one, you go to the .git folder, and it's a fresh clone. So there's a single pack file. It's about 8 gigs in size. And that index was about 16 megs, like I had said before. And if I won't sit here and make you watch all of it, but you can see that it's going to keep counting up. And there's about 3 gigs of sources there, 112, 113,000 files or something. Now I've got the same repo that I've cloned, but it's not mounted. So right now you won't see any contents in here on GVFS. And so this is that same working directory. There's only one file in there. The Git attributes file. When we cloned it, we went ahead and put that file on disk. We actually made sort of one major constraint of using GVFS is we don't allow any clean or smudge filters, because that makes it really hard to reliably project a file if you can arbitrarily change it as soon as you check it out. But so there's one file in there. I go to the .git objects folder, and you see that one object was laid out. That's that Git attributes file, and I have about an 80 megabyte pack file. That just has all the tree objects for the 2 most recent commits in it. And that's it, right? So from that, and I'll show you the contents of, oops, let me go into that folder. you look at the contents of the sparse checkout, and this is where a lot of that magic happens. Right now, it's saying there's just that one file, right? And so Git's happy that only that one file exists on disk, and that's all it cares about. But let me go ahead and now mount, and you'll see there's nothing in here except for that file. I'll go ahead and mount GVFS, and I'm going to mount it with a flag to show its debug spew in a window so that we can kind of see what's happening. Part of what it's doing right now is it's checking with the server to make sure that its client version is not too outdated, and the network here is giving me a little trouble. I'll give it a minute. Once this is done mounting, what it's going to do is it's going to then examine the Git tree for the current commit that's checked out, and from that we can project the whole shape of the working directory. Of course, if it doesn't connect, that's not going to work. Some of the challenges that we've had to face in making this work is just that index file is a real pain point. It's in the Windows repo, it's 400 megabytes. And whenever we hydrate a file, we have to update the index to clear the skip worktree bit on that entry. And there's 3.5 million entries in there. The way Git normally updates the index, and this is mounted, I'll get to it in a sec. The way Git normally deals with index changes is it always writes the new index to an index.log file, makes whatever changes it needs in there, and then copies it over, renames it to delete the old index and overwrite it with the new one. Rewriting 400 megabytes every time we want to change one bit is very inefficient, and so we've had to get very clever with how we do that, but still play nice. So we just create an empty index.log file. We parse the index file and remember the offsets of every entry, and so we can quickly get to it and update it. So we've had to do a lot of optimizations there. Anyway, so this is now mounted, and oops, there's the debug window. And now I'll enumerate, and you'll see that it's asking the server for the sizes of the children entries in that folder, but there's all the entries now. And so even though it was empty, and it still is empty, if I unmount GVFS, there's still no files in it. But now I'm enumerating it, and you can see all the contents in that folder. And I'll just go a few folders deep here and show you, there's some more children, and there's some more, and it's downloading it's asking the service for the sizes, because in NTFS, when you enumerate, you have to specify the sizes on the files, and so we had to ask the service for those. And let's go into this one here. And now I'll open one of these files, and so let's look at, I don't know, Git constants. And you see here it went and downloaded that loose object on the fly, and there's the file. So Notepad doesn't know any better. It's all just right there. And I'll open another one. Make some changes and save it. And run git status. And it knows that I've changed that file, so everything still kind of works like normal. And you might have noticed that as I ran git status, it downloaded one more file. That was git status always wants to see your git ignore file, so that's the one it went and downloaded. So let's go ahead and unmount this, and we'll see what state we're left in. Now you see there's some actual files sitting on disk here, right? I have the git attributes from before, the git ignore that it just downloaded, and then the one file that I touched, it had to create the folders to contain them, or the two files, and there are the two files. Now those are just real files on disk. And if I look at the sparse checkout, all the files that we hydrated are now in there. So now if you go and edit any of those files, Git looks at them when you do a status or a checkout or a commit or whatever. And so everything just works as normal. So like I said, we're still working on optimizing the performance of all the commands, but it's brought us a long way. So what's next is, we keep plugging away at that performance. We have, on that giant Windows repo, we have a handful of users who have been our brave early adopters. And they keep telling me when they find some corner case where we go and download 3.5 million blobs, and we go fix them, and we keep getting closer. Actually, this weekend, we're going to be deploying to another round. About 150 people this weekend are going to be coming into that repo. And over the next 2, 3, 4 months, we'll be bringing in quite a lot more. There's 4,000 people that'll end up in that repo by the end of it. So that's pretty exciting. We're just right on the cusp of rolling this out to a very large team. Beyond that, so my priorities in what to do for GVFS are, number one, we have to be totally correct in terms of the file system operations and the Git results. Correctness is number one. Perf is the next thing. We got to make sure that developers are not getting blocked waiting on the performance there. And after that, we're going to start picking away at tools that use Git and make sure that they're happy. And the top two are going to be Visual Studio 2017 and GitK. Those are the two of the most common ones that our own users use. And the rest will kind of depend on demand. We've actually just changed Visual Studio 2017 so that it shells out to git.exe for all of its internal Git operations. And that's what we need in order to support these tools. GitK does the same. And so now it's just a matter of making sure that they kind of play nicely and they don't go off and start hydrating files that they shouldn't and things like that. We definitely are hearing demand that we should support GVFS on Mac and Linux, and so that's something we're looking hard at. If anybody out there knows about file systems on those platforms, come talk to me. We're definitely hiring. And that's it. I think I have a couple minutes for questions, if anybody has any. Out there, yeah? Could we modify git grep to do server-side search? For the most part, we've tried to leave the behavior of Git unchanged, and just make it so that the file system makes it brings things in as you access them. And so for something like, for those sorts of historical tools, commands in Git, it poses an interesting challenge. With git log, for example, it just tries to walk through all the objects locally, and it could be kind of painful. So part of what we did there to make it work nicer is we actually prefetch your history of commit objects because they're tiny. And we can just download them all in one pack file, and git log will have access to them, at least for the commit history. For the blob history, it has to go and look at each blob individually. And we've talked about prefetching certain blobs in order to make that better. I haven't really thought about something like that, of taking a command that you would normally run locally and shuttling it off to the server. It's an interesting idea, but we haven't gone that approach yet. Let's see, out there, yeah? Yep. So I have a hard time hearing, but you're talking about if you were to do a global search. Yes, so if you were to do a global search across that whole repo, it would be very painful. It would go in and download everything. The thing is, in a repo that's that big, 99% of people don't work across all the sources. The vast majority, what they do is they only have to work in some 2 or 3 levels down subfolder. That's where they spend all their time. And nobody ever clones the repo and builds the whole thing, right? That would be madness. It would take forever. And so what people do, the actual workflow that people have, is they will download the build outputs from the last official build that succeeded, and then they'll go into some subfolder and they'll work in there. And the typical size that we see is people will need 50 to 100,000 files, and we can hydrate those pretty quickly. And so in reality, that's where you're going to be doing your searches. Is the same set of files that you're going to be building are also where you're generally going to be searching. We also actually have, the Windows team has a lot of infrastructure built up around their code base, and they actually have really fast server-side searching capabilities. So if you do need to do a search for things beyond where you're working, there are very good tools that we have for that. Over there. Right. Sure. So yeah, the question was about limited refs. Actually, we didn't modify Git to enable limited refs. We only modified how we respond to the info refs. And so we didn't have to change the client side at all. But the question was, when you have limited refs, how is that different than just having forks? In a lot of ways, it looks similar. You know, that you see a limited number of the branches. But the difference is, you know, forks kind of solve a trust problem. Whereas with limited refs, we're solving a scale problem. They're kind of tackling different, their core goals are different. And the benefit is, you know, with limited refs, if you're in a team of people that are all trusted, they're all, you know, everyone's authenticated and on the same team and all that. If I want to see somebody else's branches, I just go to the web and favorite their branches, and now I clone them, and we're all in the same repo. So there's fewer hurdles in sharing our code with each other versus compared to forks. So I'm all out of time here. Happy to take questions.